AP Calculus BC, Unit 7 Day 11. This little note sheet kind of run down what is going to be covered on this upcoming test, which is a lot of stuff because it's mostly review of AB material. So we put a lot in here. Probably what would have covered two and a half chapters in Calc AB. So as we go, I'm also going to emphasize which parts are which part. So there's going to be two parts to the test. One of them is calculator, one of them is no calculator. Part one is graphing calculator, and it will be 34% of the test. And part two is no calc, and it will be 66% of the test. So part one's about a third, part two is about 2/3. As I kind of review these topics, I'm going to put a number on the left side indicating which part it is on. So you can say over here, part. So for instance, Riemann Sums will be on part 2, no calculator. It kind of makes sense. They're kind of more by hand problems. There's different Riemann sums, left in, right in, and midpoint. Trapezoid is not called a Riemann sum. It's a different kind. And I would draw pictures of these. One of the questions you'll be asked is if they're over or under estimates. And I don't try and memorize this. I just draw a picture. So if you draw, a picture of an increasing concave up, left in is going to be underestimate, no matter if it's concave up or down. So if it's increasing, it's definitely going to be an underestimate. And if it's decreasing, it's going to be an overestimate for left in. So it has to do with either increasing, decreasing, or concavity. Right end is going to be an overestimate if it's increasing. And so if it's decreasing, it's going to be an underestimate. But you just draw a picture and confirm it. Midpoint and trapezoid depend on the concavity. Now, trapezoid is pretty easy to see. If it's concave up, it's going to be an overestimate. And so then if it's concave down, you could draw a picture of concave down to confirm this. It's going to be an underestimate. Midpoint's probably the hardest one to figure out. Midpoint uses the halfway height. And if it's concave up, there's more that it's missing than it's there's more underestimate than overestimate. It's a combo. So if you draw a picture, just write if it's concave up, it's going to be an underestimate. And if it's concave down, you could draw a picture and it's going to be an overestimate. Now remember the formula for trapezoids, and the trapezoids are usually going to be kind of vertical in nature. There's two bases, they're parallel to each other, and they're sideways. And then this is the height. And so the area of a trapezoid is the average of the bases times the height. It's really it's like a rectangle. And I've shown this before where you can move things around and it does become a rectangle. So rectangles are base times height. There's two bases, so you average them times height. Easy to remember. So over under estimates. Anyways. Okay, so that's going to be on part 2. Evaluating definite integrals with absolute values is going to be part 2 also. If it's a linear absolute value, you could use geometry. If it's not linear, and even if it is linear, you have to break up the integral at the zeros, the x-intercepts of the graph, because that's where it's going to change positive, negative. And then you can use a line check to figure out if it's positive, negative, and then fix the negative. The shortcut is this technique, but using a table to organize it and to also take out the repetitious work. So you just integrate the function without the absolute value, find the antiderivative, don't need the plus c, and then you plug in the starting points, and then if it's a motion problem, turning points or zeros, and then you find the distance between them, and you add it all up, and that would give you the value. And that also is the way you do distance on motion problems. So we are going to have one-dimensional motion problems on part 2 also. Speeding up, slowing down is when velocity. Speeding up is when velocity and acceleration have the same sign, so they're acting together to speed up. And a line check, two line checks above and below each other is the best way to do this. Slowing down is when velocity and acceleration are acting against each other. They have opposite signs. They're acting in opposite directions. Displacement is the final position minus the initial position. We could integrate the velocity to find that. And if we're doing that already for distance, then you can use that table for both of these, which really makes the table work out. Distance is the integral from beginning time to end time of the absolute value of velocity, or in other words, speed. And the shortcut, like I illustrated above, is we take time and we integrate velocity, and that gives you the position function, maybe without the c. And you have your starting points and your turning points where velocity equals 0, very similar to this. And then you find the distance between them. But you could also do this minus the first one to get your displacement. So you can use that table to answer both of those questions. Straight area problems are going to be part 1 when you have a calculator. And you could do it with vertical slices. Vertical slices where everything's going to be in terms of x, and it would equal y top minus y bottom in terms of x, though, because it's going to be dx, and you're going the x direction, x left to x right. So that's the technique. It's not a formula to memorize. Or you could do horizontal slices. And horizontal slices would be x right minus x left. And you always want right minus left to make sure it's positive. You should always get positive area dy, and then it'd be y bottom to y top for your limits. So know how to do area. Volume by cross section will be on part 1, and this is where they have similar common cross sections like squares or rectangles or half circles or equal out triangles or other things, just writing some, I don't know, equilateral triangle. You can memorize the formula if you want, root 3 over 4 side squared, or you could just break down the 60-60 triangle into 30-60-90 triangle and figure it out yourself. So the volume is going to be in terms of some common area formula for the shape that they all have in terms of x, or in terms of y. This is not an option. You don't get to choose if you do x or y like you do on all the other volume area problems. You have to do x or y. It changes the shape based off the directions of the slices, the cross sections. Length of curve is one new thing to you guys from AB, and that will be on section 1. And we derived it. It's very similar to the other length of curve formulas we have for polar and parametrics. It has a square root. It has two things inside being squared and added. This time, just the derivative. So that's the formula. You should know it. Solids revolution. These are volume problems, so this will be on part 2. So you're going to be able to use a calculator for it. Disk washer method is the slices are perpendicular to the axis of rotation. So perpendicular to the axis of rotation will always give you a disk washer slice. And the volume of it, don't memorize this. Look at the picture. It's a short cylinder, pi r squared, area of the base times the height, which in this case will be the thickness, dx or dy. Okay, and then you're going to integrate them. So That's a disk. Washer means there's a little hole inside, and you got to just subtract a smaller version of one, and that's your washer. So draw good pictures. Don't try to memorize that. It will be very obvious. Shells, or tree rings, if you want to sort of associate them with something that maybe you understand, are these nested sort of shells. Now they each have a radius and a height, and if you cut it open, you get a rectangle, and it has the height, but this distance right here is actually the distance around the top edge. That's the circumference, 2 pi r, of your shell, and then it has a thickness to it, dx or dy. And so the volume is the area of a rectangle base times height, 2 pi r h, times the thickness, dx or dy, depending on the orientation of the slices. And then we integrate them. Now, these are always going to be parallel to the axis of rotation. You will get shells if you slice it parallel to the axis of rotation. So you should know what to expect depending on the way you slice it. You shouldn't be kind of waiting to find out after you draw the picture, because then you'll probably just draw it in some weird way. Mean value theorem will be on both parts 1 and 2. So mean value theorem, the idea, I wouldn't memorize it. I wouldn't memorize this formula because you mess it up, is we find the area under a curve and then we flatten it out. And now it looks like a rectangle. The height of that is what we're looking for here. So then if we have the area under the curve and we have the area of the rectangle, if we just divide by the base of the rectangle, we'll get the height of the rectangle, which is what we're looking for. There's also this other C x star thing, this guarantee of the mean value theorem that says somewhere along the curve, the actual value will equal the average value at least one time. Now, there is a mean value theorem for derivatives, which comes in handy when you have a derivative and you have the original function. And you could use this approach for it and give the same answer, but this cuts the work down a little bit. It's just going to be the slope of the secant line between the endpoints. So if you find the slope between the endpoints, that slope is the average of all the slopes in between. And then there's this idea that there's this value of c somewhere between the endpoints. The actual derivative equals the average derivative at least once. And this c value right here also has to be between the endpoints, including the endpoints on this one, not on this one for derivatives, because derivatives are two-side issues, and the endpoint, you don't have two sides, you only have one side. Okay, rate models will be on part 1. And so we have the current amount. I mean, they're really just fundamental theorem of calculus part 1 application. We have the current amount, which equals the initial amount, or some known amount. And then we're going to accumulate all the positive changes, the entering rate, positive rate, from 0 to some time t. So we're going to accumulate all the positive changes. I like to use E generically, but it might not be E. Minus all the leaving changes, the losses, you might call that the leaving rate. So it really is just, you are now what you were before, plus the accumulation of all the changes, but now we have positive changes, negative changes separated. So it's really fundamental theorem of calculus. You're often asked about the derivative, the overall rate, which is just the entering rate minus the leaving rate. Is it increasing? Is it decreasing? You're often asked to find the absolute max or min, which I would use extreme value theorem. Use the endpoints. Critical points are going to be from setting this equal to 0. And then do a table of them. So, all right, top 10, number 10, fundamental theorem of calculus part 1 and part 2. Part 1 is going to be on fundamental theorem of calculus part 1 will be on both parts of the test. And it just says that if you integrate a derivative, you're going to get the original function. And then if you plug in limits, which you usually have, you can plug limits in, top first, bottom second, subtract. And then we usually use this when we have information with the derivative and we know one of these points and want to find the other, and usually with the calculator. That's why it would be on part 1. The part 2 is when you take the derivative of an integral. And we usually put a different variable in here than what's here. And there's usually some kind of expressions, functions in the limits. And so what happens is the derivative of undoes the integral, and then you can just plug the limits in, top first, bottom second, but leave some space. The derivative of what you plugged in has not been taken yet, and it's an inner function, so it's a chain rule issue. So make sure you multiply by the derivative of what you plugged in, only what you plugged in, because usually there's a much more complicated expression here, and everything's taken care of except for what you plugged in. So that's fundamental theorem of calculus part 2. So that's a good just rundown of everything we've covered in this chapter, quite a bit of AV material and what parts of the test it will be on. And may help. Hopefully this will help you prepare for it. All right, that's it.